Okay, so today we're going to be talking about MANOVA, multivariate analysis of variance. So first of all, what can MANOVA do? It can assess significant differences between several dependent variables. So in the case that you have more than one predictor, as well as more than two, um, or several rather, um, dependent variables, you're going to want to use this test MANOVA. So what it needs in terms of assumptions, we have four different ones: independence, random sampling, multivariate normality, and homogeneity of covariance. And we will assess those today once we start running our code. So when should we use this? Well, when you have a design that necessitates that with several dependent variables especially. So let's begin. And I will talk about the experiment that I'm going to run once I bring in my data set. So first we're going to open various packages here, including reshape, read Excel, car, MV norm test, pastex, MV outlier, mass, and ggplot2. I don't think we actually end up using ggplot, but we end up using boxplot instead, which is the function, not the package. But regardless, so first of all, we're going to use this function here to create a variable called MANOVA using the read Excel package, and this is where my data is located. As you can see, it popped in there. So we're going to briefly view that real quick. So we have group, job satisfaction, job performance, and PAS. Ignore these. Those were from some correlations that I ran previously. So let's say that three different groups were created according to level of autonomy: high, medium, and low. And what we're interested in is, I guess, as far as our hypotheses is concerned, is we're interested in, hey, does group have a significant effect on job performance and job satisfaction, a significant main effect? And if I didn't say so before, PS refers to perceived autonomy support. So that's our hypotheses. So first we're going to factor this variable here. We're going to factor it according to group, and then we're going to level this variable as well and specify the labels of high, medium, and low. C in both cases refers to the list that we're creating. Now we're going to begin by creating some box plots to briefly visualize the data as we begin. Essentially, we're specifying the predictor and the outcome variables in each of these, and we're specifying where the data is located. And the only thing that's changing between these three lines is our outcome variable. So moving on, we're going to run some summary stats using the by function. Here we specify our data, and all these three are going to be the same except with small variants. I could have combined them into one, but I did not in this case. In one line, that is. So we're going to specify the outcome variable, data, and our predictor variable, stat_desc, provides us with a descriptive output, and basic equals false. So we're going to run these three lines, and that creates our summary stats there. So now we're going to check an assumption that I mentioned, in this case the homogeneity of covariance. So what we're going to do is we're going to split the data by group. In our first part here is we're going to use the by function again. We're going to specify the data, and now we're going to specify, well, we don't want to do that. We're going to undo that. Not sure exactly, just moved it a little bit. But what we're doing 2 through 4, we're specifying the columns here. We're interested in columns 2 through 4. And then COV at the end, that produces the covariance output. And what we're interested in here is a variance ratio of 2. It looks like we have somewhat comparable variances, possibly a violation, but those would have to be computed. But we're going to come back to that later. So now what we're going to do is we're going to transpose some of the columns, because to do the Shapiro's test, which assesses the assumption of multivariate normality, we're going to need to transpose some of the columns. So we're doing that by calling a variable high, and we're specifying what row numbers we're interested in, as well as what column numbers we're interested in here. Now we're going to use the transpose function here to transpose the rows and columns. And we're doing the same exact thing here for medium, but we're specifying 11 through 20. That's what rows we're interested in, and then 2 through 4 columns. And we're using the transpose function in one line here. And we're going to do the same thing for low. So now we're going to run the Shapiro test. High, medium, and low. And to get a visual representation, as far as our Shapiro plot is concerned, we're going to produce this. We can look at this a little later. As far as interpretation is concerned. So moving on, now we're going to set the contrast to run our MANOVAs. So high versus low, medium versus low, and then we're going to C-bind. We're going to bind the contrast into a singular line. And now we're going to do some binding as far as predictors are concerned, and we're going to create 3 different models here and run 3 different MANOVAs. So for the first one, so first of all, we need to do this because according to the general format of running a MANOVA, it's outcome predictor like typically, but we're going to combine in this case all of our outcomes into one. So in this case, we're binding job satisfaction, job performance, and PAS. And outcome 2, we're binding job satisfaction and job performance, which is our main interest here according to the hypothesis that I presented at the beginning. And now we are going to talk about outcome 3, which is we're talking about job satisfaction and PAS. But again, we're mainly interested in outcome 2 here in line 91. So moving on, we're going to run the MANOVAs for each model that we have created, and we're going to call that model 1 MANOVA 2 and MANOVA 3. And now we're going to be interested in MANOVA 2 because that is the bind of the outcome variables that we're interested in. So moving on, we're going to summarize these models that we created, and we're mainly interested in this because as we look at the various assumptions that we have ran, looks like we have definitely violated, just from eyesight, we have definitely violated the assumption of normality. So as far as this is concerned, we're omitting the test equals here, and what that does is runs a Pelias test, so which is the most robust, in terms of violating the assumption of normality. So we're going to be most interested in this output, but in these we're going to be running different test statistics, Wilks, Hotelling, and Roy's largest root. So we're going to run these, and again the only difference is we're running different test statistics, and I will not run those for the future MANOVAs that we do run. So I'm going to run all these lines and they produce output. And now we're going to run an actual ANOVA on our summary model. And we're going to summarize these as well, MANOVA 2 and MANOVA 3. And as you can see, I omitted these different test statistics here. So moving on, looks like we ran that. So now we're going to do the same thing and run ANOVAs. And these are going to be type 2s that we primarily run because we do have a balanced design. So now that we ran our MANOVA, it's typical that we follow up with a univariate analysis. In other words, we're essentially conducting an ANOVA with our differentiated models. And we're going to execute the names, and we're primarily interested in this output, but we will come back to that. So now we are going to move on to the final phase, which is a discriminant function analysis. So to do that, we're going to begin by creating model 2, which looks like we haven't used that variable name yet. I was just double checking. So we're going to use model 2, linear function job satisfaction group. So we're going to run that. And these are going to create separate linear models so that we can view contrasts and things like that. And model 3, which includes job performance and group. And model 4, I'm only replacing PAS. So now we're going to summarize each of those models by running summary.lm and then the model name. And now we're going to use the IDA function, and we're going to produce a variable called DFA, and this is going to take the general linear model format, except we're adding each of our predictors in this case. So we have outcome variables rather. We have group, which is our predictor, and then we're adding each of our outcome variables and then specifying the data name. And this is very helpful in performing a follow-up analysis as opposed to the univariate analysis that we did before, because we're um, able to look at the effects that dependent variables have on each other. And I'm not going to go into it in too much detail, but essentially we're sort of running a reverse MANOVA here, where we're saying, hey, instead of our predictor predicting our outcome, can the outcome predict the predictor? So now we're going to view the model, and we're going to type in predict DFA, and that allows us to use the function to look at the discriminant scores, and now we're going to plot that as well. So if you want a visual representation of your discriminant scores, which is very tough to read, that produces that. So now we're going to move backwards a little and talk about interpretation. So first, we will look at, I guess we can start with the assumption of covariance of matrices. And if we're going to look at our output here, it looks like we possibly do violate the assumption of covariance of matrices because we're looking for a ratio of 2, like I said previously. So in this case, it does look like we violate that. I do randomize my data, so that is just a corollary of that. Moving on, if we look at Shapiro's test as well, for the first one we ran, we do not violate it. For the second one we do, and for the third one we do as well. And these violations are going to necessitate us using PALIs, as I stated before. So if we want to move back to Shapiro's AQ plot that we produced, what the output does is the numbers in red indicate that we possibly have an outlier. And as you can see, we have multiple ones here. So moving forward, something that I could do is remove these from my data set previous to running that after I found them to be outliers. So moving on. Now we're going to look at our different MANOVA outputs, and I'm going to focus on the output that points us towards my hypotheses. So MANOVA 2, as I stated before, included the output of job satisfaction and job performance. So if we look at that output here, it looks like we do not have significance. So we can conclude that we can fail to reject the null in this case. But moving forward anyway, if we did want to look at the univariate analysis of MANOVA 2 model, we could look at that as well. And in this case too, the significance of our F values have not been achieved. So moving on to the discriminant analysis, a couple things we're interested in here as I scroll through. So I think one of the biggest things that you're interested in here is this output right here. And we're going to want to look at the coefficients as well as proportion of trace. In other words, what percentage of variance has been explained. And if we look at the discriminant function of variate 1, it looks like we have a very large portion, around 98%, and only 0.024 for that. And another thing we want to look at here is these columns here, which essentially produce regression coefficients. And one thing that you do want to look at is kind of the trend of these different columns, and it looks like in both cases we have dissimilar numbers, as in positive and negative, large and fairly small. In this case, positive and negative 2 in this one as well. So that's going to point us towards our discriminant function plot, which in my opinion, it's much easier to interpret whether there are discriminant functions occurring looking at this output here. But if you were to look at this, you're going to want to isolate variate 1 and variate 2, which is very difficult, and I would recommend pulling it into different plots. But that is outside our jurisdiction today. So as we can conclude, we fail to reject the null hypotheses in our case. group did not have a significant effect on job satisfaction or job performance. Thanks.